Hello, everybody. Today we're going to be talking about logistic regression, and let me just share my screen with you so we can get started. All right, logistic regression. This video is going to be some of the basics of logistic regression and some general terms and initial issues that we'll need to deal with. Oops. There we go. All right, so some of the basics. Logistic regression differs from linear regression, which we've been talking about almost exclusively in terms of regression, in that it deals with dichotomous outcome variables. That is, yes, no answers, live or die, vote or don't vote, anything that comprises two categories. Now, that said, you can use logistic with multi-category dependent variables. That's called multinomial logistic, but that's beyond the scope of the course. And to be honest, I rarely see those analyses anyway. So what does logistic mean? Well, logistic or logit refers to the type of the use of a log type transformation on the dependent variable. So that log piece is what it means. Now, I know that we've talked about logs and things like that in the past, and some folks don't have a background with logs. Don't worry about that. The mathematics aren't particularly important with what a log is, as it won't have much to do with how we interpret things. We also talk about odds. That is the likelihood of one thing happening over another, or likelihood of one outcome over another, rather. So for example, among 100 eligible voters, we might have 60 who voted and 60 who did not. We would say there that the odds of voting would be 60 over 40, the people who voted over those who didn't vote, for an odds of 1.5. That's all what we're talking about with odds. It's basically how many more people voted than didn't in this example, or what proportion more. All right, some other basics. When we talk about logistic regression, we're not necessarily using odds on their own, but we're using what are called odds ratios. That's the odds of one group compared to the odds of another group, or the odds of one group over the other. So as an example, we might have among those 100 voters, 50 who were under 30. Under 30, we'll call those a younger group, and then the rest were 30 or more. We'll call those generously the older group. 33 of the 50 younger people voted in this, in whatever this election was, giving them an odds of 33 over 17, or 1.94. But only 27 of the 50 older people voted in this case, giving them an odds of voting of 27 over 23, which it comes out to 1.17. The odds ratio, we can take the odds of younger people voting over the odds of older people voting. We just divide them by one another, and it gives us an odds ratio of 1.66. A couple of ways to interpret this. One thing you can do, you see in some textbooks, is you take 1 minus the odds if the odds are greater than 1. And this tells you a proportional difference, or which you convert to a percentage. So 1.66 minus 1 is 0.66. That would suggest that young people are, the odds that young people vote are 66% greater than the odds that older people vote. I prefer to just interpret it directly. Young people are 1.66 times more likely to vote than older in terms of this election. Just some of the different interpretations. Now, these ratios, if they are exactly at 1, it means that there's no difference. If they're lower than 1, it means that we have a difference favoring the group on the bottom. So logistic regression focuses on initially the log of the odds ratio. That's where that log piece comes in. And for our example, if we had run this in R, our output would give us a coefficient of 0.51. And that's simply the log of 1.66. So everything is going to get reported as the log of our odds. Now, nobody really thinks in terms of log values, so it's going to be useful for us to convert them back to odds, but that's a thing that we'll need to recognize when we get our output. It's going to be in terms of log odds. With log odds have positive and negative values, whereas odds themselves do not. Positive value in this example would mean that the group in the numerator of the ratio that was the young people, would be more likely to vote than the people in the denominator, that is the old people. A value of 0 would mean that the odds were exactly the same for both of the groups, because that would correspond to an odds of 1, the log of 1 is 0. A negative value would mean that the group in the denominator was more likely to vote than those in the numerator. That would be an example where older people were more likely to vote than younger people. We can easily convert the log odds that we get from these analyses to odds through a process that's called exponentiation. It's a mathematical thing that it just unlogs it, basically. If you look at an old-time calculator, it'll have a key on it called EXP, and that's just for taking the log and converting it to a regular number. So if you exponentiate 0.51, and this is the R code you would use to do it, you get 1.66. Odds are also related to probability, and we can think of them in terms of probability. You can see the difference in terms of how we calculate them. For example, if we look at the odds of a younger person voting, it's 33 over 17, or 1.94. In terms of the probability, the numerator is the same, the number of people that voted. The denominator, though, is just out of the total number of younger people, 50 in this case, and you can see that for the older one as well. So why can't we use linear regression in these cases? Why can't we just run regression as we always have and not have to learn something new? Well, the easy answer here is that the relationships are no longer linear. We can't model this sort of relationship that we have with a straight line. In this graph, we see that. We see a continuous variable called survival predicting an outcome that's either a 0 or a 1. One thing we can clearly see is that that regression line really doesn't capture the shape of the relationship at all. So we can't use regression here. We'll talk a little bit more about regression, and we'll see how these types of dependent variables that are dichotomous look in terms of assumptions and things like that in the next video. Now, the relationship that we're actually dealing with is best expressed with what's called a sigmoidal curve. A sigmoidal curve is an S-shaped curve that provides a better fit for our data. You can see a graph here using a sigmoidal curve, and you can see how we're catching a lot more of the points in our graph there with that S-shaped curve. For those who are into math, this is one version of the sigmoidal curve is the logistic function. Other versions of sigmoidal curves are the hyperbolic tangent, the arctangent, and of course the Gudermanian function. I know absolutely nothing about any of those except it said that on Wikipedia. All right, one last piece that we need to talk about in this video is data preparation. We need to just make sure and verify before running our analyses that our categorical variables are defined as factors. Sometimes you'll have categorical variables that are just coded as 0 and 1, but they aren't actually, but they're actually numeric variables. So what I've provided here is an example of some code creating a new variable. This is a variable called physician's recommendation, which we'll take a look at in the next set of slides. It's basically a yes or no question that was coded initially as 0 and 1. I want to take the old variable, which was numeric, that was the one called physrec, and I want to create a new variable called physrec_f. I use that labeling to let myself know that this is a factor. And then I want to tell it what the levels were. It was originally coded as 0 and 1, and then give labels to those. When we do that, it's useful to run a summary, and you'll know that things worked if your summary now has no and yes there. So we'll play around a little bit with this coding in the upcoming exercises. All right, that's it for this. That's it for this set of slides for this video. The next video will be logistic regression and running it as a linear regression.